So the eye. The eye consists of, for optical purposes, the relevant things are there is a cornea. There is an aqueous humor too that the eye is surrounded by. There's a pupil which lets light in. There's the eye lens. Then the inside of the eye is filled with a vitreous humor. And then there is the retina. So the photosensitive cells, photosensitive means sensitive to light. The photosensitive cells of the eye lie along the retina. So for us to be able to see something, an image of it has to be formed on the retina. All of these things have indices of refraction that vary slightly. So if the cornea's index of refraction is a little more than water, 1.35 or so, that of the lens is about 1.4. So light bends mostly when it goes from air to through your cornea, and then it bends a little more. The fine tuning is done by the eye lens, which can change shape, and the change of shape of the eye lens is done through the ciliary muscles. So the ciliary muscles control whether the eye lens is relaxed or tensed. So if I'm trying to look at a distant object, usually the eye lens is relaxed, the normal eye lens, and that is to say that rays that are coming from very far away are approximately parallel. So the distance between the lens and the retina is the focal length of the lens. Okay? So if I'm looking at, on the other hand, a nearby object, and once again I want to form an image of that object on the retina, then what happens is that the ciliary muscles tense the lens. By a process called accommodation, you can then focus in on an object that's close by, and once again have an image formed on the retina. Okay? So when we talk about the eye, the normal eye, you talk about a far point and a near point. The far point is the furthest away an object can be and still be in focus. The near point is the nearest an object can be to your eye and still be in focus. That is to say, objects further than the far point are not in focus. Objects nearer than the near point are not in focus. Okay? So for a normal eye, the far point is basically extremely large, infinity. But for an eye that has if you're nearsighted or myopic, then you have a far point that is something finite, 2 meters, 1 meter, 50 centimeters. Okay, and how far away your far point is determines what the power of corrective lenses is that you need to put in order to be able to focus on objects. For the near point, the normal near point is about 25 centimeters. And if you're either born with an eye where there is some defect, like this distance is too great, or you are aging and your eye lens is less able to accommodate, something called presbyopia, then what's happening is that nearby objects are no longer in focus, and my near point has moved to something greater than 25 centimeters. Okay, so once again, what then I have to do to correct my vision is to say, if I take an object that's nearer than that, I need corrective lenses to be able to focus on that object. What happens in each case? Okay, so this is the normal near point and far point. All right, so myopia, which is nearsightedness, what happens is that the far point is not infinite. So this again, as I've said last time, it happens if your lens is too converging and you have an image that instead of being formed on the retina is formed in front of the retina. So the way you correct this is to make those light rays converge less strongly. So you put in a little diverging lens. So this is corrected using a diverging lens, which allows the rays to diverge a little bit more so that they converge only on the retina. So the object, the image moves from in front of the retina to on the retina. Okay, so in terms of how you think about doing this with the corrective lens, what you're doing is that you're saying, I have this object which is at this object distance. The furthest I can focus on an object is at my far point. So I need to create an image of that object at the far point. So here's my object. The first step in this is to take that object distance and create an image at the far point. So the image distance is the far point. Since this image is in front of the eye, that far point is a negative distance, okay, because the image is forming in front of the lens. Object distance, of course, you're trying to focus on an object that's extremely far away, so you can take object distance to be infinite. That means the corrective lens you need to use has to have a focal length basically equal to the distance to your far point, okay? Right, so this tells you the focal length of your corrective lens is the distance to the far point. The negative part of it tells you it has to be a diverging lens. So when you're myopic, the doctor tells you you have a minus power. And the minus comes from the fact that you're correcting your vision using a diverging lens. Refractive power. All right, so that is defined as 1 over the focal length. The units of this is diopters if you express your focal length in meters. So remember this. If the focal length is in meters, the result you get for power is in diopters. So suppose I tell you that you have a nearsighted person who wears contact lenses with a power of -2 diopters. What is the far point of this person? So you want to say, okay, look at the equation I have on top. I say P is 1 over F. I know P, so I'm given P is equal to -2 diopters. So the first step you can do is find the focal length of the lens. What will the focal length of the lens be? -0.5, because it's going to be 1 over P, which is 1 over -2 or -0.5 in what units? Meters. So if you like, your focal length is 50 centimeters. So what is your far point? That is your far point, okay? Because remember, our equation to get the far point was 1 over object distance plus 1 over image distance is equal to 1 over F. What I want my object distance to be is infinite. So this gives me that 1 over my object distance goes to 0. So then what I have left, if this goes to 0, is that I have 1 over image distance is 1 over F. But what is my image distance in this case? I want my image to form at my far point. Or rather, image distance is -d far. So it's going to be d far, image distance is equal to F, right? So this is equal to F. That is to say, d far is -F, but F is -50, so this is going to be +50 centimeters. So your distance to your far point is 50 centimeters. So you're basically always using this lens equation, thin lens equation. The other defect of the eye is farsightedness, which means I can't see nearby objects. So in this case, I have that my eye is not converging enough and there's an image that's forming behind the retina. What you want is that your lens should correct this so as to form the image on the retina. So you need to correct it with a converging lens to make the light rays converge more. So what the lens is doing effectively is, okay, ideally I should be able to see an object at 25 centimeters, but I can't. So the object is located here. What I can see is an object located there. So my lens, what it's doing, my corrective lens is taking the object located here and creating an image of that object at the point where I can see it. So here's your object distance where the object is actually located. The image distance is the distance to your near point. So you have, here's your close by object, this is the object distance. Here's your near point, that's the image distance. So your object distance is whatever it is. The image distance is the negative distance to your near point. And that tells you the power of the corrective lens. So let's do an example of this. Suppose your near point, instead of being 25 centimeters, is 50 centimeters. So for example, let's say my near point is, let's say 50. The numbers will work out to be easy. What is the power of the corrective lens that I need in order to? So say you go home now over Columbus Day weekend and your parents use reading glasses. You can prescribe reading glasses to them by doing the simple test. Okay? How do you do the test? You get somebody to pick up a piece of paper. Okay? And it's out of focus. You move it till it's in focus. Alright, so that's your near point. So given somebody's near point, which you can measure by measuring the distance from the eye to the point where the object is in focus, how would you provide corrective lenses? You do want the object, you want it to be in focus when it's at 25 centimeters. So this D near should be negative image distance. So now when I use my thin lens equation over here, I have 1 over object distance plus 1 over image distance is equal to 1 over f. 1 over object distance is 25 centimeters plus 1 over image distance. Remember, image distance is negative 50 centimeters. So what is 1 over f going to be equal to? What is 1 over 25 minus 1 over 50? 1 over 50, right? Because you can write 1 over 25 as 2 over 50. So it's 2 over 50 minus 1 over 50 or 1 over 50. So this tells me plus, so I get two important things from this. One, that the focal length is positive, so I need a converging lens. Two, I know the focal distance is 50 centimeters, so f is equal to 50 centimeters. What is the refractive power of this lens? So first, to get refractive power, you should change that to meters. So you write 50 centimeters as 0.5 meters, 50 times 1 over 100 centimeters. So then P is equal to 1 over F, which is 1 over 0.5 meters. So it's plus 2 diopters. So you know your parent's power is going to be plus 2. Alright? So you know when you go to the ophthalmologist, they just have all these lenses and they put them in front of you and they see when it's in focus for you. Okay, there's one other defect of the eye that I won't talk about very much, but that's astigmatism. Astigmatism, when the ophthalmologist writes your prescription out, it's usually written as a cylindrical number. And that's because the problem is that your eye is not perfectly spherical. So the image formation in one direction is different from the image formation in this curvature, and this curvature are different. Okay? I am, for example, astigmatic. It's not very serious, or the only problem is that you see things double. You see a double image. Okay? That is to say, the different images formed, you typically see blurry images, double images like this. Yeah, and the way you correct this is by putting in a lens that is also not symmetric. Okay? And it has the correction in the right direction. So slightly different focal length in different directions.